Okay, welcome back. So last time we discussed the log minimal model program, and we ended with showing that after a divisorial contraction or after a flip, the discrepancies can only get better, not worse. So now we want to define the actual models that we would like as the outcome of the log minimal model program. The only subtlety is, as we saw in a few examples last time, is what do we need to say about the divisor? So we know we want some, if we have some pair x comma delta, we want to define log minimal models, log terminal models, log canonical models as something birational to x, but we need to be careful about picking our divisor. Um, so okay, well, let me give the naive definition, kind of the absolute case first. So let's say we start with some x comma delta, which is some log canonical pair projective over B. Then we can talk about x comma delta being a minimal model or a log minimal model in the abstract by just saying that and maybe you want to say relative to B or over B, but usually that's implicit. If x comma delta has DLT singularities, and kx plus delta is nef over B, so is f nef. But okay, and then but what we really want is we want to say if we're given an x comma delta, we want to produce its log minimal model. So we need a definition for kind of a version of log minimal model with respect to a different pair rather than just in the absolute sense. Okay, so what properties should it have? So the first property, well, we want it to be birational, so let's just draw it in a diagram. We want it to be birational over B. So we want some y that sits over B, and we want y to be projective. So let's assume that the morphism G is projective. Maybe you can work in the proper setting and let G be proper, but we'll stick to projective. We want to be able to define the divisor on y to just be the push forward of the divisor on x. And so we saw that for that to be the right thing to do, we need to assume that phi extracts no divisors. Meaning that phi inverse contracts no divisors. So phi can only contract divisors. There are no extra divisors on y. And given 2, we can now just define the boundary on y to be the push forward of the boundary on x. Okay, and now we need to say something about the discrepancies, and that this is the important point. So we need to give some condition on the discrepancies. I'll write down the condition, and then we'll discuss multiple reasons why this is the right condition to consider. We want that the discrepancies on x comma delta are less than or equal to the discrepancies on y comma delta y for all phi exceptional divisors. Okay, so there's several reasons for this. One, we know this is true when phi is some composition of divisorial contractions and flips. So we know that if all our phis are coming out of the log minimal model program, this will be true. More philosophically, we want our models to not have worse singularities than our x. So we know that all of this theory works for KLT pairs, DLT pairs, or whatever class of singularities we want to stay within. We want to make sure that our models don't leave that class of singularities. And since the measure of singularities is given by discrepancies, we want to say that the discrepancies on y are no worse, and that's exactly what this inequality is saying. Another reason, let me write down over here, if phi is a morphism, say we're in this special case, maybe we just have extremal contractions and no flips. Then we can write, what is this condition 3 saying? Condition 3 is really saying that we can write down kx plus delta as phi upper star ky plus delta y plus sum of ai ei's, where these ei's are phi exceptionals, and condition 3 is saying that the ai's are greater than or equal to 0, i.e. this term is effective exceptional. So we'll see in more detail in a second what this means, but essentially this means that the ring of sections is the same, because when we pull back, we're adding some effective exceptionals. Those don't contribute any sections by the negativity lemma, and so this tells us that the log canonical sections are the same. So that's another way of thinking of condition 3. But now we can actually hope for even more than 3, because we actually saw that last class we saw that if you have an exceptional divisor, or if you just have a divisor lying over x, that's in the locus where phi is not where phi is not birational, is not an isomorph. Sorry, in the locus where phi is not an isomorphism, then the discrepancies actually get strictly better when phi is a flip. And similarly, if phi is an extremal contraction, and we have some divisor whose center is in the exceptional locus of phi, then again we have the same thing, that the discrepancies have to get strictly bigger, because we actually have an exceptional term, a non-zero exceptional term in this sum. We can't just have coefficient 0, but again by the negativity lemma. And so we can hope for something even better. We can hope for condition 3 prime, which is that we want our models to actually satisfy that a ex comma delta is strictly less than ae y delta y. Again, for e phi exceptional. Okay, so this condition then 3 prime, in the case where phi is a morphism, is saying that we actually have some wiggle room there. We really have some divisors appearing. Okay, and then you should think of the difference between 3 and 3 prime. Like 3 prime comes from the actual log minimal model program. It comes from divisorial contractions and flips. 3 comes from this final step where if we assume abundance conjecture, then we're supposed to have a semi-ample linear series given by kx plus delta. And under the semi-ample linear series, now we could pick up some exceptional divisors with coefficient 0, because these are going to be the exceptional divisor. These are going to be the divisors where kx plus delta is 0, where when we restrict, we actually get 0. And so you should think of it as like 3 is what you get after you run the log minimal model program and then apply the abundance conjecture to get a base point free linear series, and y is the output of that, while 3 prime is like the output of just divisorial contractions and flips. And that's essentially our definition. So let me scroll up and write it. So our definition, let's say f from x comma delta to b is a, just to be safe, let's assume x comma delta is already log canonical. So it's a log canonical pair, projective over b. Then we'll say that a pair y comma delta y with delta y equals the push forward of delta, and where y fits in this diagram. Like this, satisfying, well, let me phrase it like this, is a let me organize like this, is a weak log canonical model. And denoted W LCM x comma delta over b if it satisfies 1, 2, and 3 above, and ky plus delta y is gnef. Okay, so that's our first step of model. So just recall again, 1, 2, and 3, projectivity, extracting no divisors so that the push forward divisor is the right thing to put there, and that the discrepancies get no worse. And then 2 is a log minimal model. Or sometimes people drop the word log, or sometimes people call it a log terminal model and denote it LTM of x comma delta over b, all various conventions. If we further assume that x comma delta is DLT, so we're in the terminal, not canonical case, and it satisfies 1, 2, and 3 prime, so now the discrepancies are getting strictly better for exceptional divisors. And the same assumption that ky plus delta y is gnef. Okay, so if we start with something DLT and we have a model where the discrepancies get strictly better and ky plus delta y is gnef, we call that a log terminal model, LTM x comma delta over b. And then finally, 3, just the usual canonical model. Or, well, I should still say log. So a log canonical model rather than a weak one. If it's a weak log canonical model, and we actually assume that the log canonical divisor is ample. Okay, so I'll stop there for a second. There are various types of models. Are there any questions about these definitions? Okay, so our first observation is that, so in this definition, we just assumed that the discrepancies are no worse or get strictly better for phi exceptional divisors. The idea being that this is an easier condition to check. But it turns out that this is true actually for all divisors, and so we actually know that the singularities of the pair y comma delta y are no worse than the singularities of x comma delta. So in particular, we know then that for log terminal model, because we assume that x comma delta is DLT, then following the proposition I'm about to write down, then we'll actually know that y comma delta y is DLT, for example, or KLT, etc. So so here's the exact proposition. So I won't keep rewriting the assumption, so just fx comma delta to be as above. And let y comma delta y be a weak log canonical model. Then for all divisors, E lying over X, the discrepancies, the discrepancy of X comma delta of E and X comma delta is less than or equal to the discrepancy of E for Y comma delta Y. Okay, proof. So basically we want to do what we did in this green case where phi was a morphism, except phi is not necessarily a morphism. So we just make it a morphism by resolving the indeterminacies. So pick some W that resolves the indeterminacy. So it's going to sit over X and Y, and it's going to commute in a diagram like this, where P and Q are birational. And this was F, this was G. Okay, and then assume also that the center on W of E is a divisor. So pick some resolution of indeterminacies that sees the divisor that we're working with, that we want to show, that we want to prove something about the discrepancies on. And now let's just write down our discrepancy equation for both sides. So KW is P upper star KX plus delta plus, let me call it EX, or maybe I should call it AX. So the discrepancy divisor for X. And then we have the discrepancy divisor for Y. And now the observation is just that A EY delta Y minus A EX delta is just the coefficient of E in this divisor AY minus AX. And so what we want to do is show that AY minus AX is effective. And that'll let us conclude that the discrepancies all can only go up. So let's take the difference of these two equations and then rearrange a little bit. So when we take the difference, we get 0 equals P upper star minus Q upper star plus AX minus AY. And so what we get is that a divisor B that we'll just call P upper star minus Q upper star is AY minus AX. So it's the thing that we want to show is effective. Okay, and now we're going to use the negativity lemma for the morphism P. So the observation, so what do we need for the negativity lemma? We need to know that one, P lower star B is effective. But when we push forward, so P was this map down to X. When we push forward to X, we only see the divisors that are phi exceptional now. And our assumption is that on our definition of a weak law canonical model is that for phi exceptional divisors, the discrepancies can only go up. And so we know that P lower star B is effective by assumption. And the only places where the discrepancies can go down are the extra divisors like E that don't appear on either X or Y. And so we know that P lower star B is effective. On the other hand, we want to look at minus B, and we want to show this is Neff. That was the negativity lemma, was that if minus B is Neff, then P lower star B is effective if and only if B is effective. And then we'll conclude. So let's check that minus B is Neff. What's minus B? Well, minus B is Q upper star ky plus delta y minus kx plus delta. Minus P upper star. And so we want this to be Pnef. But now let's think about the curves and the fibers of P. So for curves in the fibers of P, this P upper star kx plus delta intersects them 0 because it's a pullback. So if we take some curve class in the fibers, some effective curve class in the fibers of P, then P upper star kx plus delta psi is 0. But on the other hand, ky plus delta y is assumed to be Neff because y comma delta y is a weak log canonical model. And so if we intersect our curve class with the first term, with this Q upper star, well, by projection formula, this is ky plus delta y dot the push forward. But now we're taking some effective class and pushing it forward, so or some pseudo-effective class and pushing it forward, so it's still pseudo-effective. And so this is greater than or equal to 0 by assumption. That y comma delta y is a weak log canonical model. Okay, and so now by the negativity lemma, since minus b is Neff and p lower star b, or minus b is p Neff and p lower star b is effective, then b is effective. And so the discrepancies on y are bigger than are greater than or equal to the discrepancies on x. So we're done. Okay, any questions about that? Okay, and so kind of the corollary, which I'll just summarize, is that the singularities of a weak law canonical model are in the same class as those of X. So the singularities plausibly can even get better, but they can't get worse. Okay, and now we want one more type of model, which is a good minimal model. So a log minimal model or a log terminal model. Sorry, y comma delta y is good if ky plus delta y is semi-ample. Again, relative to our base, so it's f semi-ample. Or another way of saying it is that the abundance conjecture predicts that all minimal models are good. But this is a useful definition to have because we don't know the abundance conjecture, but it turns out that by work of BCHM, we know the existence of good minimal models. And in a lot of other cases too, I guess you can produce a good minimal model without actually knowing the abundance conjecture by carefully picking your minimal model. Okay, and maybe the other observation is that if y comma delta y is of log general type, so if k plus delta is big, then we actually know that that any minimal model is good by the base point free theorem. So we already showed that the base point free theorem implies abundance in the general type case. Okay. So we can re-summarize the log minimal model program, or like the various conjectures now more succinctly in this language. So if x comma delta is a DLT pair that's projective over B, then there are a sequence or you can say maybe all sequences of kx plus delta flips and extremal contractions. Such that the composition is a good minimal model. I should say either such that the composition either is a good minimal model, or we're in the other case. Sorry, I was only thinking the non-negative Kodaira dimension case. So such the composition one is either a good minimal model or is a Mori fiber space. So either we have an extremal contraction down to something lower dimensional, or we have a good minimal model. And then I should say maybe part of the conjecture is that, so in the case of surfaces, if you remember from like 2 months ago now, what we showed was that you either end up with a surface where kx is nef, or your ruled surface, and kx is nef if and only if some multiple if and only if it's actually effective as a Q divisor. So if and only if some multiple has sections, and you get a ruled surface if and only if your Kodaira dimension minus infinity. So if and only if you never have sections. And so the natural generalization of that if and only if of when you're in the two cases is that you're a good minimal model, like you end up with a good minimal model if and only if kx plus delta is pseudo effective, and so here if and only if kx plus delta is not pseudo effective. Okay, and we're here pseudo effective as a divisor means you're in the closure of the cone of effective divisors. So far we've only been working with the closure of the cone of effective curves, but you can make the same definition. Right, so that's maybe one way to summarize all the conjectures in the minimal model program. And again, here maybe the full conjecture is that so the full conjecture is really for all sequences of flips or divisorial contractions, you either end up with a good minimal model or a Mori fiber space. Okay, any questions? Okay, so I want to talk a little bit about kind of the uniqueness question, both for canonical models and also for flips, and the existence question, and we'll see that they're actually very closely related. So let me just write down the result. Let's say we have x comma delta to b as before, and y comma delta y is the log canonical model. So now not the weak one, the actual log canonical model for x comma delta over b. Then y is the proj over b of the relative log canonical ring. Okay. And the proof of this, we write down the same kind of hat diagram with our W. So here's our log canonical model Y. It's the morphism, the rational map phi is resolved by this W. Everything's happening relative to B. And now let's write down a pair structure on W. And here we'll kind of see what you should do when you have a rational map that does extract divisors. So in this case, the inverses of P and Q extract divisors because P and Q could contract divisors. So let's write down the following. Take the strict transform of the divisor of the boundary on X, and now we're going to add the reduced exceptional divisors. And we saw this briefly a few months ago. That if you want to give, or one way to give a boundary structure to some log resolution is to give the reduced exceptionals. It's not the only way, but yeah, let me just write it down that these are reduced exceptionals, meaning comes with coefficient 1. Okay, and now because x comma delta has log canonical singularities, then this is equal to the pullback of kx plus delta plus some effective p exceptional stuff. Because log canonical singularities tell us that the discrepancies are greater than or equal to -1. So when we add 1 times each of the exceptional on both sides, we get something effective. Okay, and now let's write down. So this will be our boundary on W, is this delta W. And now let's write down the log discrepancy equation for Q. And now the point is that the same is true for Q. That here we also just have effective Q exceptionals. All right, and that's essentially because of our assumption that that phi doesn't extract any divisors, and that yeah, so since phi doesn't extract any divisors, then the kind of the difference between the pair delta and the y and the pair delta w is all exceptional. And also, since y is the log canonical model, we know that for all divisors, the discrepancies just get bigger, and so we get this equation basically. So this is by definition of log canonical models. Okay, and so now we use these two equations to just compare sections. So on the one hand, p lower star of OW m kw plus the round down of m delta w. This line bundle or this divisor is the pullback plus something p exceptional. So the sections are the same as the thing we're pulling back. On the one hand, so that's from the first equation. And then from the second equation, we can push forward to y, and we get that the push forward to y now of mkw plus m round down of delta w is, again, we have something that's pulled back plus q exceptionals, and so we just get the sections of the thing we're pulling back. And so then we can just write down some equality of produce, because now we see all the sheaves are the same. So y is the proj over b of the direct sum of g lower star oy m ky plus the round down of m delta y. This is from the definition of log canonical model, because we're assuming that ky plus delta y is G ample. And so this is equal to, well, now by the second equation, this is, let me just write down some equalities with what's inside the proj. So this algebra is equal to G lower star Q lower star of OW M KW plus the round down of M delta W. But then Q compose G is the same as P compose F. So this is the same as F lower star P lower star OW M KW plus the round down by commutativity. And this is equal to just the push forward of the log canonical on X by the first equation. Okay, and so that's what we want to show, that our log canonical model is the proj of the relative log canonical algebra. So in particular, this tells us that it's unique because it's given by this single proj. It doesn't depend on y at all, and it also tells us that the existence of a log canonical model is essentially equivalent to finite generation of this algebra. So then we get that LCM x comma delta over b is unique if it exists. And it exists if and only if the algebra this sheaf of algebras is finally generated. Because of course, on the first side, y equals this proj of the log canonical ring for y. Well, here we're assuming that ky plus delta y is ample, so that side's finally generated. So then we get that the other side's also finally generated. Okay. And then another corollary of this is that basically, if we add effective stuff, if we add effective exceptionals, then the log canonical model doesn't change. So more precisely, let's say we have a morphism phi from x prime to x, such that we have a log canonical pair x prime comma delta prime, where kx prime plus delta prime is equal to the pullback of kx plus delta plus effective phi exceptionals. Then the log canonical model of x prime delta prime over b is equal to the log canonical model of x delta over b. Okay. And so this tells us that kind of if we're blowing up, then from the point of view of the log canonical rings and log canonical models, kind of that we can pick any boundary divisor on x prime that we want that satisfies this equality, that kx prime plus delta prime is phi upper star kx plus delta plus effective phi exceptionals. And one good choice is to just put coefficients 1 on all the exceptionals, but it's not the only choice. But in particular, we don't want to put really small coefficients on the exceptionals. For example, we don't want to put coefficient 0 on the exceptionals because that'll change the log canonical ring and it'll change the log canonical models. They might not even have the same dimension. You might, yeah. Okay. Any questions about all that stuff? Okay, and now this brings us back to existence of flips, and the observation is just that by definition, a flip is a log canonical model relative to something. So that's the main observation. So let me write it as a proposition. So let f from x to y be a flipping contraction of a log canonical pair. Then 1, The flip exists. Sorry, let me say the flip, if it exists, is the log canonical model of x comma delta relative to y. So existence of flips is equivalent to existence of log canonical models in a special case. 2, because it's a log canonical model, then it exists if and only if we have finite generation. So if and only if the algebra is finally generated. And then 3, since it's the log canonical model, is unique. Okay. So the only thing really to prove is that a flip is a log canonical model. We already saw a log canonical model exists if and only if this algebra is finally generated, and that log canonical models are unique. So proof. So suppose we have a flip. So here's our flipping diagram. And we have f plus over here. Then well, we have our divisor. Delta plus is the push forward of delta. This morphism phi contracts no divisors because actually it's just small. Sorry, it extracts no divisors because it's just small. It's a flip. And we also know that. So we know that. So phi extracts no divisors. And has no exceptionals. So it contracts no divisors either. So conditions 1 and 3 are automatically satisfied in our definition of a weak log canonical model. We also know, conditions 2 and 3. So we also know that kx plus delta plus is ample. Sorry, is f plus ample. This is the definition of a flip. That we're taking some curve that was kx plus delta negative, and we're contracting it, and then we're extracting a curve that's kx plus delta plus positive. So kx plus delta plus is f plus ample by definition of a flip. And so this tells us that x plus is the log canonical model, basically by definition. And so then from this previous proposition or theorem, then we get parts 2 and 3. Then we get parts 2 and 3 that the flip is this proj, and so it exists if and only if this proj makes sense, and that flips are unique. So we want to be able to say that we want to relate running some particular nice steps in the minimal model program on x comma delta to the minimal model program on some divisor inside of x and some divisor inside of that divisor. So we need to relate like KLT pairs in dimension n to KLT pairs in dimension n minus 1, or DLT pairs to DLT, etc. So to do this, we need adjunction. So let's just recall the kind of classical version of adjunction that we've used a million times, which is that if S in X is some Cartier divisor, then we have this standard Kx plus S restricted to S is Ks. the standard equation. And then more generally, if we have some boundary on x, then we can consider kx plus s plus delta restricted to s, and we'll get that this is ks ks plus delta restricted to s. Okay, and so we want to use this type of procedure to say that something about the minimal model program for the pair x s plus delta implies something about the minimal model program, or maybe back and forth, for the pair s comma delta restricted to s. And now the strategy might be something like, well, what happens if I start running my minimal model program on x comma s plus delta? Well, first of all, my divisor is a little special here because I'm assuming I have this Cartier piece s. But then I want to be able to say that I can't have an infinite sequence of flips on x comma s plus delta, because those would give me an infinite sequence of flips for the pair s comma delta restricted to s. That's the type of argument you want to make. And then you want to say, well, then by induction on dimension, I know there are no infinite sequence of flips in lower dimension, and so there are none for the pair x comma s plus delta. But then you need to make sure that all your flips are kind of happening inside of S, and so you need to work harder, and this is why you need to pick your extremal contractions very precisely. But the first step is to let us actually relate the singularities of x comma s plus delta to these singularities of s comma delta restricted to s. And then more importantly, in general, it's too much to ask for that we have this Cartier component in our boundary, in our s plus delta. And so really, we want to be able to write down some formula for adjunction when we're restricting to some divisor that's not Cartier, basically any integral of a divisor. And so to do that, we need to define what's called the different. So let me go back for a second and say, where does this equality come from? This is really an equality of equivalence classes. So this is an equality of linear equivalence of Cartier divisors. But it actually comes from like a canonical functorial map between line bundles. So there's a functorial residue map, which goes from omega x twisted by s to omega s. Where does this come from? Well, one way is to just see that you have a exact sequence like this, and that this exact sequence is basically functoriality properties of omega x tell you that this exact sequence is functorial in S as well, and that this map, this R, is just the map in this exact sequence. And then you can also compute this map in local coordinates, assuming that S is smooth. You can compute it as, well, if S is smooth, then having, let's say X and S are both smooth. So in the smooth case, then having a differential form, a top form with poles on S, this is like something of the form f times dx0 over x0 wedge up to dxn. So it has poles only along x0 equals 0. So S is cut out by x0 equals 0. And what's this residue? Well, this is kind of the usual residue from, I don't remember if maybe I already covered this earlier in the class. So if so, sorry about that, but I don't remember. So it's this usual formula for the residue, saved from complex analysis. Then you have to check that this kind of local formula glues together, gives you a unique functorial map that comes from Serre duality, and et cetera, et cetera. But the point is that you really have this unique map. You don't just have a linear equivalence of divisors. Okay, and we're going to use that to define the different in general when S is not Cartier. So let me make a simplifying assumption, which is that S is normal integral of a divisor. So it should always be an integral of a divisor to make sense of the different. and to make sense of adjunction, but let's assume that that it's actually normal, just a simplifying this assumption, and then I'll say a little later what you should do when it's not normal. Let's essentially normalize. And now, since we have this pair, we have this x that's normal, we have this s sitting inside of it that's normal, then we can find some z in x, some subset such that x minus z is, say, smooth, and that s minus z is Cartier. So we can find some z so that this is smooth and this is Cartier. And then we want to assume a little more. We also want to know that, because we have a pair here, we have a pair x comma delta plus s. So we also want to know that delta intersect s is contained in the set z. So the z should really be inside s. Okay, so there's some high, in this case, codimension 2, we can take z to be codimension 2, subset where it contains the intersection of delta and s, and it away from it, x is smooth and s is Cartier. And let's also assume that s and delta share no components. Of course, this is important anytime we want to restrict one divisor to a different divisor. If they share components, then things can go wild because there's going to be some self-intersection. So we want to assume everything doesn't share components so that we can control the intersections. Okay, so we're in this situation. We pick the subset Z. Now, let me give the first definition of the different. Now on the complement of Z, we have a residue map. We'll call it R S minus Z. And this residue map goes from omega x of S restricted to S minus Z. So it's some vague divisorial sheaf, but we're restricting it to the locus where S is actually Cartier. And now on this locus, because S is Cartier and X is smooth, then we have this residue map, which is an isomorphism with omega on S minus Z. Okay. And so now we can take its some large enough power. So now we know that M, we have this this log pair. So we know that mkx plus S plus delta is Cartier for some M. So pick that M where it's Cartier, and now look at that tensor power of the residue map. So that tensor power of the residue map will be well, it'll induce an isomorphism from the mth reflexive power of our line bundle of our divisor on X, because multiplying Weil divisors is the same as taking reflexive powers of the Weil divisorial sheaf. So we have the reflexive power but again, we're restricted to S minus Z. And now this is isomorphic to, because on this locus, everything's a line bundle. So this is isomorphic to omega S minus Z mth reflexive power. And again, here I can say that that's just the mth tensor power as well, because on this locus, S is Cartier, so it's actually a line bundle. Okay, so we have this isomorphism like this, but now since S is normal, we can find an S0 inside of S, such that well, all these sheaves are actually line bundles on S0. And the codimension of S minus S0 is greater than or equal to 2. So that's the important part. That's where we use we use normality. So we know that if S is normal, then it's smooth in codimension 1. It's non-singular in codimension 1, and so we can kind of extend this R to some rational isomorphism between line bundles on a subset of codimension of a subset whose complement is codimension 2. So now we have this rational isomorphism on S0 between line bundles. But anytime you have a rational isomorphism between line bundles, there's going to be unique divisors that you're twisting by to make it an actual morphism. So this extends to some isomorphism. Like this, where delta S0 is some Cartier divisor. So again, what's delta S0? It's just the divisor of zeros and poles of this rational isomorphism R. And so now, because S0 has complement codimension at least 2, then we can just push everything forward to S and get an isomorphism of A divisorial sheaves. And this is unique because S is S2. And when we push forward the restriction, we just get the restriction. When we push everything, if we restrict to this big open set and then push forward, that's the same as just the usual restriction, again, because they all agree on this big open set. And so we get this isomorphism like this, where delta S is the push forward of delta S0. Okay. And now delta S is essentially our different, except that we multiplied by M. And so our different is delta S divided by M. So this is some a priori. It's not. Well, so what do we know a priori? Yeah, a priori is just some V divisor. We don't know anything because we know that delta S0 is Cartier on S0, but then when we push forward, we just get some V divisor. It doesn't have to be Q Cartier, so it's just some Q divisor. But the point is that this gives us an actual divisor rather than just some divisor class. So it's really a divisor. Okay, so that's the first definition of the different. That was kind of cumbersome, but it tells you that this different is some canonical construction that you associate rather than just some divisor class. It's really a canonical divisor, and all these operations are functorial because we can extend away from codimension 2. We can extend all these maps. But that's not really useful for actually working with things. So the second definition, which if you think a little bit about it, you'll see is equivalent. It's just rewriting this equality. So this isomorphism Rm, once we've extended it to all of S, we can rewrite it into a linear equivalence of divisors and define the different to be a divisor satisfying that kx plus delta plus S restricted to S is Q equivalent to ks plus the different. So in particular, this tells us that even though the different itself doesn't have to be Q Cartier or anything, ks plus the different is a Q Cartier divisor because kx plus S plus delta is Q Cartier for our log pairs. So ks can be just some V divisorial sheaf. The different is just some V divisor, but their sum is still Q Cartier from the construction. And now the third definition, which is really just a way to compute the different, maybe it's not really a definition, but the third way to think about the different is that you take a resolution and try to compute it using a resolution. Because on a resolution, we can make S be Cartier, we'll make X be smooth, and then we have the usual residue. So here's what we do. Let's say that we have a log resolution of our pair x s plus delta and let's pick our divisor on y, our boundary, so that ky plus delta y is the pullback of kx. Sorry, we wanted s as well. So ky plus sy plus delta y is the pullback of kx plus s plus delta. So define sy and delta y. With one, it's the pullback, and then two, the push forward of sy is s, and three, the push forward of delta y is delta. So that'll be our boundary on y. And now we can compute the different as follows. We can write down adjunction on y because y is smooth, and we've log resolved everything. Then on y we just have that delta y restricted to sy is the different. And now the point is that to compute the different downstairs, we just push this forward. So you take a resolution, you pick the right boundary structure so that there are no discrepancies for this boundary structure, essentially. And then you compute the different there, where it's just usual adjunction, and then you push forward. So that's the claim. So then different on S of delta is the push forward of the different upstairs. And it satisfies that the pullback of ks plus delta, plus the different, the pullback of ks plus different along the restriction to s of this resolution f is ksy plus the different on sy. Or maybe in keeping with the simpler notation, this is just delta y restricted to sy. The nice thing about this third way is that this lets us where we're going, which is what inversion of adjunction actually is a statement about discrepancies, is relating the discrepancies of x with the discrepancies of s. So the discrepancies of x comma s plus delta with the discrepancies of s comma the different. And these type of birational maps where you pick the boundary so that you have the push forward, so you have the push forward of the divisor as the divisor and the pullback of the log canonical as the log canonical. These are these resolutions where the discrepancies are the same. And so what this tells us is that if we want to compute discrepancies of s comma the different, we can take a log resolution of x and then compute the different of the strict of this sy upstairs and then compute discrepancies there. That's what these equations tell us, is that we can compute discrepancies upstairs. And so since we're running out of time, I just want to give one example of actually doing a computation with the different, and then we'll move on next time. So here's an example. Let's say we have a projective cone over a conic. And we have S is one of the lines through the cone point. Then if we take a resolution here, wrong way. If we take a log resolution of this, then this is a computation I think that we did. But what do we get? Well, we get our conic curve here. It's inside the total space of the normal bundle of the curve inside of P2. The strict transform looks like that. So there's our SY. What's the pullback? Well, the pullback of KX, it turns out, is just KY. This resolution doesn't change the canonical. It's one of these canonical singularities. It's an A1 singularity. And the pullback of S is the strict transform plus 1/2 the exceptional. And so upstairs are delta y is 1/2 the exceptional. That's the divisor that satisfies the equality that the push forward is the divisor downstairs. Well, there's no other delta downstairs, so then the push forward of this exceptional is 0, so that works. And also that the pullback of the log canonical is the log canonical of this delta y. Well, that's what these two formulas are telling us. So then this tells us that the different on sy of delta y, well, that's just the restriction. So E dot sy is just that 1 point lying over the cone point. And so this different is 1/2 times this P lying over the cone. I don't know what's happening. Okay. And so then when we push forward, this tells us that the different of this line through the cone point of the 0 divisor, we don't have any extra divisor, is 1/2 times the cone point. And so here we see kind of as a Q divisor, class is just 1/2 a point because this line is P1. So all that matters is the degree. But it's not just 1/2 a point. It's actually, we have an actual divisor. It's 1/2 of the particular cone point. And we see that it's supported exactly where the divisor passes through the singularities of X. And so you should think of the different as measuring something about how the singularities of S and the singularities of X kind of interact.